Oh man, got a clap and everything, thanks. Yeah, thank you, Ryan. As Ryan said, my name is Jordan Parmer, and I work as a software engineer at a company called Osberg here in Oklahoma City. And one of the things that we do at Osberg is a lot of data processing. And so we ran into, we were trying to research ways of doing data processing, and we started off kind of with one technique that I'll get into later. Then later, as we learned things, we heard about reactive streams. And so we started using reactive streams. And so that's what I'd like to talk about today. Now, before I get too far, how many of you know what reactive streams are? We'll start there. Okay. Oh, great. Okay, this is good. Okay. Let's see. How many of you do data processing as your main, line of work? Okay, so 2 or 3 people. Okay, so I'll try to have to win the rest of you over then. Yeah, this talk will mainly be focused on intensive data processing, but at the same time, reactive streams is not just geared toward data processing. There's actually a lot of applications for it. So if you're not doing a lot of back-end data loading or ETL stuff, this can still be relevant to you. And I just hit the screensaver. Right when I was getting ready to hit the button. Okay. So, what is reactive streaming? Okay, so this is directly from the Reactive Stream spec. It's a common mechanism to move data across an asynchronous boundary without losses, buffering, or resource exhaustion. All right, now that's pretty important. How many of you guys have just tried to stream data from a file or over a network at all? Yeah, I mean, a lot of us have. Whenever you start doing that in volume, you're going to run into some problems. First of all, you might start out on a single-threaded process. And in that case, you got to think about, well, how are you going to buffer the inputs? How are you going to handle processing it and then writing it out somewhere else? What happens whenever you want to pass data across thread boundaries? That gets a lot more complicated because then you've got shared state you've got to worry about, and you've got to worry about how the threading model looks and the thread pools. What do you do whenever you have an error in the middle of your stream processing? How do you handle that? All those things become problematic, and you end up writing a lot of boilerplate code, even if you're using one of the Java libraries that can handle streaming from a file or whatever. You still end up writing quite a lot of boilerplate. And so the reactive streams spec and API handles a lot of that for you, and as we'll see, it's a very nice abstraction to load data on an asynchronous way, and it takes care of all the buffers and resource utilization. So here's some common use cases. Especially in big data circles where you have high volumes of data that are unbounded. And what that means is that I don't necessarily have a finite amount of data I'm trying to load. It might be something that's streaming live. So you're Twitter and you have tweets that you're streaming, and that's coming at you just ad hoc, and it's completely unbounded. The akka-stream, or I'm sorry, the reactive stream pipeline is a way of handling that kind of data volume and processing. Message queues. How many of you work with message queues at all? So like Kafka, RabbitMQ, ZeroMQ. Okay, a couple of you. Okay, great. So you might be familiar with some of these problems. If you're on Microsoft, you might be using BizTalk or whatever. And so you got a pub-sub model. And that's another thing where you might be getting a lot of data coming in on a pub-sub model. You need to process that and push it somewhere. And that comes with its own problems and challenges depending on what you're doing. That's a very natural use case for this. And then in a more traditional sense, you just have network streaming and file streaming. Some kind of more everyday sort of things. Okay. Now, if you have followed the reactive hype lately, you might have come across 2 terms, and I want to clarify this before I go much further. So there is a difference between reactive programming and reactive systems. So have anybody heard of the Reactive Manifesto at all? Okay. If you start to research this, you'll quickly come across it, and it's easy to blend the two, but they are different. So there's this thing that exists called the Reactive Manifesto, and the idea there, it came from companies such as Lightbend, TypeSafe, Netflix, and I think there's like 2 or 3 others that are involved in that. And the idea is that they are designing a spec for systems that have these 4 properties. They're responsive, resilient, message-driven, and elastic. And all that's saying is that your system as a whole needs to be responsive. So you make a request to the system, you get a responsive feedback, even under load and various conditions. They should be resilient to failure, so if you're on a cluster and a node goes down, it can still be responsive. Message-driven, so you're passing around messages that are immutable. And then elastic, so under load, it can scale out to that load and down again. So that makes up what's called a reactive system. And if you're interested in that, look up the reactivemanifesto.org, and it'll kind of go into the details of what that is. That's a little bit different, though, than what we're talking about today with reactive programming, all right? Here's kind of a side-by-side comparison of the two. Reactive programming is application-centric. So we're at the level of CPUs, threads, and local resources. It's per process execution and event-driven. Reactive systems, that we just talked about, is more of the system view. So how do all the pieces in your system or your cluster coordinate together? What's the cohesion like there? And message-driven. So we're interested in the part on the left today. Okay. So how do we use it at Augsburg? So here's kind of our use case. At Augsburg, when we first got into data processing, we were, several years ago, we were very much in an early startup stage. And so we needed to very quickly get large amounts of data into a product. And most of us at the time were comfortable with SQL and your traditional databases. And so we went with an initial traditional like ETL model. So we had a lot of very database intensive kind of serial processing of data. Everything was done in batch. So we would have we use Scala as our main language. We'd write like Scala loaders that would take in various files or data from other sources, load those into the database, and then every night we'd run through a really large batch database operation to kind of give us product ready data, which worked for a while. And then we hit some pretty big scaling problems. I don't know if any of you have gone down that path before, but eventually your batch operations get so long that it stretches through the whole night. If anything goes wrong in the database operation, the whole show stops. It's really hard to work in parallel with other developers in that pipeline without stepping on each other's toes. And there's dependencies between database objects, and if you take one down, that breaks another one. And so it's just a lot of problems in that. So what we started doing was moving to a more microservice approach. And we use Kafka as a message broker between microservices. And so what we have essentially is we will load up a lot of events or messages into Kafka, and then we will pass those across microservice boundaries. And so each microservice is responsible for one piece of the ETL. Oh, I got a bad connection. Is that why that's blinking there? Okay. So whenever we're talking about reactive programming for us, we're talking about each microservice is going to be using the Reactive Streams workflow. And I'll get into more detail about what that looks like, but essentially you have a data source, which for us is Kafka, and then we've got a piece in the middle which actually handles the transformations, and then we're going to write the output back to Kafka. And then after a while, it begins to look like this, where you've got a large process graph. So you've got Kafka between several microservices. Some of those microservices are going to write to a database to do like aggregation and kind of collect data. And others are just going to be a pass-through. It doesn't have any state it needs to store. It can just send it right along. So after a while, you kind of build up this large process graph. And with reactive streaming, this becomes very natural and very easy to do because each of these microservices is essentially just a reactive stream workflow. Okay, so reactive streaming is actually not an API, it's a spec for an API. And so there are many implementations of reactive streaming. So what the spec does is describe, you have something that's, a publisher of data, something that's a subscriber of data. This is how you can chain together operations. And it essentially defines an interface for what that should look like. And then any implementation goes through compliancy testing as to whether or not it fits that spec. So one of the most popular ones is by a company called Lightbend. That used to be called TypeSafe, if you are familiar with that scene. But the akka-streams API. So Dylan Forsha over there gave a talk a couple months ago about akka actors and the actor system. And akka-streams API is built on top of the actor system for akka. Now you don't have to know the ins and outs necessarily of the actor system to understand akka-streams. It's actually a very nice abstraction that hides most of it from you. But that's what it's using under the hood. And all of the benefits you would have of an actor system, you're going to get with the akka-streams API. So here's the general workflow of what this looks like. You have what's called a source or a publisher. So the Reactive Streams spec calls it a publisher, and then on the right side you've got a subscriber. akka-streams API, their abstraction of that's called a source and a sink. So I'm going to use the source sink probably through most of this. But essentially you have a source of data, and that source can come from all kinds of places. It can come from a collection that you've loaded in memory. So if you're in Java and you've got like a collection or array of data, it can come from a file. It can come from a network where you're streaming bytes into the network. It can come from a message bus, all kinds of connectors into a source. And it's lazy. So it's not going to emit records downstream unless it's asked to. And then what you can do is you can chain a series of operations that apply a transformation to the data at various stages. And then there's going to be a sink or subscriber on the other end that is requesting or gathering the output. So that's essentially where it's going to kind of collapse everything together. It produces what is called demand. So it's going to say, I need records. It pulls it from the source through the chain, and then it resolves it or materializes it into some final result. Any questions so far? Okay. So let's look at a situation without akka-streams, because there's some benefits in what you get, because there are streaming solutions that exist today. So what's the big difference? Here is a push-based system that doesn't have back pressure. Back pressure is a pretty key feature to reactive systems, which I'll go into detail about what back pressure is. But today, let's look at a traditional push-based model. Let's say you have a fast publisher, so it can do, or I should say faster publisher, because what defines fast? Let's say it does 1,000 operations a second, and it's pushing records downstream. Now let's say you run into this issue where you have a slow subscriber, so it can only process 10 operations a second. So you've got a bit of an issue there because you have something that's pushing records faster than you consume them. You've probably run into this before if you've tried to push a lot of data to a RESTful web API. You might have a lot of data that you've loaded, like let's say you took in a bunch of records from a file, or your client application is trying to push a whole lot of requests to a RESTful endpoint. And suddenly you start to get 500s back or something from the RESTful endpoint saying, whoa, I'm overwhelmed, I can't take any more right now. And so then you got to figure out, okay, what am I going to do with that? So on the client side, you're like, well, maybe I can throttle a little bit, which means you got to kind of build up like a buffer. Or you might run into some out-of-memory issues and some other stuff. You have to manually deal with that in this case. So here's one possible solution. You could create a buffer, all right? So you got a flow of pushed records, and then you'll create like a buffer. You got a queue somewhere that'll collect it. But then you have the problem of what happens if you overflow your buffer, right? So you've produced more than what you can store in memory. So one thing you could do is you can drop the messages and resend it. which might be okay, but now you've got to figure out, okay, I've dropped all these messages, and now I've got to somehow reconcile that I've dropped them. That might be okay in my scenario, or maybe I need to keep track of what I dropped so I can resubmit it later. Or I could extend my buffer. So I might say, yeah, I've got plenty of memory, I'll use a larger buffer, but I really just get back to the same problem eventually, where I'm going to, at some point, overwhelm that buffer again, and then I'm at risk of running out of memory. So one of the things that reactive systems do, or streaming does, is give us this property called back pressure. And back pressure is actually implemented in a very simple way. It switches from a push-based model to a pull-based model. And so what you do is you build your graph, in the same case where we have a fast publisher and a slow subscriber, what it's going to do is the subscriber at the very end is going to give what's called demand. And it's going to say, I can receive up to X number of records now, go ahead and send them my way. So it will signal upstream the demand saying, okay, I'm ready for the next thing now. And then at that point, the publisher can say, okay, I will respond with that many records coming back. So in this case, the subscriber might have a demand of 2. There might be 2 messages queued up. It can fit 2 more. So it's going to signal upstream for 2. And then the publisher will publish up to 2 records. It may only have 1 left, and it'll just send the 1 or none. But if it can, it'll provide up to 2 more records. All right? So I'm going to switch over and do a really quick code example just to kind of show you what this looks like. I'm going to be using Scala today just because I'm comfortable with Scala. I use Scala every day. It's still in the JVM if you're not familiar with it. You really don't want to see me write Java code because I don't do that enough, so it's going to be kind of ugly. But the Scala I'm showing you is going to be easy to read, and it's going to look almost identical to what the API would look like in Java. So I'm not going to show you anything or lean on the Java or the Scala language that will give me some sort of advantage here. So let's look at this first one. Okay. Whoa. Is the text big enough for everybody? Okay, so let's look at the left code window first. I got a very simple main function that's just going to kick off one of these demo functions here. And the only thing I do of interest in here is I have a random iterator. And what this is going to do is upon each request for next, it's just going to generate a random value. Okay, so not interesting, nothing to see there, but just be aware that I'm going to use that as my data source. Okay. All right, this is the interesting part. Okay, because we are on the actor system, the only actor things that we have to do are these next 2 lines, which is initialize the actor system. So it's pretty simple. All you do is just a new actor system, you give it a label, and then you have what's called a materializer, which we aren't going to get into too much depth because it's pretty implementation specific. But that essentially describes how it's going to build the graph and some optimization stuff. But those 2 things are fairly standard and will almost always be the same thing. Okay, so down in the code, the first thing we're going to do is describe what the source of the data is going to be. Now remember, one of the benefits of the akka-streams is that you can create a source from almost anything. It's got a very rich API from, allowing you to create it from files or network connections or all kinds of things. So what I'm going to do is create a source from an iterator. So all I do is I use the source, and this is a static function from iterator, and then I'm going to pass in an instance of my random iterator. And it's going to cap my random numbers at 1,000 on the high side. So now I have a source that will yield the type integer, okay? And now I'm going to describe the far end now, which is the sink. And the sink is going to fold the results together and add them up. Who is familiar with the concept of folding? Okay, I'm going to really quickly review it, but not too much. If you guys know me at all, I really love functional programming, and so we do a lot of folding and functional programming. But a fold is essentially a recursive aggregation. So what you do is you take one value in a collection and you apply some sort of binary operation to the next value, so in this case plus, and then once I have that result, I apply that same binary operation to the next value. So if I'm folding integers together, I'll take the first two, add them together, then the result of that will get added to the next item in ad nauseum until you exhaust the collection. Okay, so that's what we're doing here. We're gonna say, okay, all of the integers flowing into the end of the stream, the sink, we're gonna fold them. We're gonna start with a value of 0, and then here's my binary operation. Take whatever's on the left and add it to whatever's on the right. So the thing on the left is the result from the previous computation, and the thing on the right is the current item. So we're just gonna always add them together, all right? And then here's my workflow. I'm gonna take the source, and because I created an infinite iterator, it's just gonna keep giving me stuff as much as I request it, I'm going to explicitly take just 100 items. So from the source, I do a .take, and then I'm gonna apply a filter operation. So I'm gonna say, okay, for every item in this collection, we're gonna see if it's even. So we'll do a little modulus against 2, see if it's even. And then of all of the values I get back that are even, I'm gonna convert it to just a number 1, and then I'm going to run that into the fold. So essentially what I'm doing is I'm counting the number of items that are even in that 100 list. Very simple. But observe what I'm doing here. I'm chaining together a series of operations against my collection. There's not a lot of code. It reads very simply, and it's pretty straightforward. What this does is this builds a graph. So I'm not actually running anything right now. What I'm doing is I'm building an expression tree. And then once that expression tree is constructed, you run it with this command, and then that runs it through an optimizer that's gonna, create the actors for that thing, set it up in memory, and then it will materialize the final value out of it. So at that point, when I say run with, it's going to run that. And if you're familiar with futures, it's gonna do that asynchronously, and then eventually when it finishes, I'll get a result back. All right, so let me make sure I save this. So over here, I'm gonna run this. I don't know if you can see that on the bottom there. Most of the time running it is just firing the JVM up. Okay, so you can see at the bottom, count 43. So out of the 100 integers I got, 43 of them were even. I can run it again. This is actually the slowest way to run it, but okay, in that time I got 47 of them, okay. So this is a very simple workflow, all right? Source, a bunch of transformations, and then a sink. Any questions on that? Yeah, pretty easy. Okay, now the cool thing about akka-streams is that, I used the word graph earlier, you're building composable graph components. And so the really neat thing is that these become like Lego pieces all of a sudden, where you can chain them together and form a really huge streaming graph. And you can reuse those pieces of the graph in different locations. So you can, they might work from this graph, might work in this graph. And all you have to do is make sure you match the inputs and the outputs. So in this example, a source has no input but one output. So if you have that collection of integers, the output's going to be an integer. Then the sink has an input but no output. There's a thing called the flow, which is like a middle piece, input and output. And then you've got fan-ins and outs and all sorts of things. So then kind of going up one level more complicated, you can have a composite source. So that just means that you have put together a graph, and then the sum whole of that graph can be a source to something else. So the sum whole of that graph put together can have one output. You can have a composite flow, so you can have a whole lot of flows put together that now become like one whole piece. And you see what we're doing here. We're just building a composable graph structure that we can snap these things together in all kinds of different configurations. And then as you see here, taken even a level higher, You can have graphs within graphs within graphs. So it's pretty cool. All right, so let's look at that. So taking what we did before, all right, so same idea. We're going to do the same workflow, but what I'm going to do is I'm going to create a flow object to handle the determination if it's an even integer or not. So I'm going to construct a new flow. It's going to take an integer as the input, so that's what that type parameter is. And then I'm going to apply the filter that determines whether or not it's even. And I'm going to go ahead and map it to the value of 1 if it is. And then down here, nothing changes, but all I do is I say, okay, via that flow. So what it's going to do is once it comes out of the source and it takes 100, it is going to run it through this flow. And all of this works because the input types and the output types line up correctly. So as you can see in my comments, the source is emitting an integer. The flow expects an integer on the left, and then on the out, you're going to get an integer out. And then my sink expects an integer in, so I can connect those together. And so if I were to run it, I'm going to get the same sort of thing. Oops. Okay, so I get a count of 45 in that case. Now, what's cool about this, though, is that we can build graphs using a DSL language. And this is where it gets pretty cool with the akka-streams. So let's say I want to count I want to emit a certain amount of integers. I want to count the evens and the odds, and then gather how much I have of both. Well, suddenly my logic's a little bit more complicated because I can't do that with a single filter. I'm either going to get the evens or the odds in a single pass. So how do I do both at the same time with the same stream of data? So one thing I can do is use a graph where the data coming in will stream and then fork in the two different directions that can have independent computations and then get folded back into together. All right. So this is a little bit more of what we do typically. So to help me, I'm going to create a helper class called counts, and the helper class is going to have two members. It's going to have an even count and an odd count. So the Scala does it a little bit different than Java. You don't need all the getters and setters, but just bear with me that you got an even and an odd count as an integer. And then I'm going to provide a way of adding two count objects together so that I can accumulate them. All right. So kind of create a little monoid there for those FP people out there. Okay, so here's what this looks like. I'm going to have two flows. An even flow, which is what we saw before. Instead of yielding a 1, though, what I'm going to do is I'm going to transform every even into a count that has a 1 on the even side and a 0 on the odd side. So what I'm going to get at the end of the flow is a whole bunch of those helper class instances that either have a 1 or a 0 on the even and odd side. I'm just going to get a whole bunch of those, and then I'm going to add them together. Okay, so same thing for the odd flow. It's going to just be the opposite of the even filter, and I'm going to put a 1 on the odd side. And here's how akka-streams lets me do this. I can build what's called a graph. Now, my one gripe about akka-streams is the graph syntax is a little bizarre to set up, just because it's just kind of a little noisy in my opinion. I know why it's that way, but that's my only kind of grump about it, is like this stuff just gets a little noisy. But what I'm doing is I'm essentially saying I'm going to build a graph, and I'm going to use this sink on the outputs, and then you can use a DSL for how the pieces in that graph communicate. So here's what we're doing. I'm going to say, okay, take my source, and you've got this operator here that's a tilde arrow, kind of the tadpole operator. I think they call that an edge is the DSL name for it. And you can use that operator just to point to the next stage in the workflow. So I have my source that's going to go to a broadcast input. So up here, I've created a fan out operator. So it takes one input and will fan out to two outputs now, which is what I want. I want to fork my workflow into two pieces. And then once I'm done with that, I want to merge them back. So I create a merge point where I'm going to say, okay, I got two inputs and it's going to be one output. So if you look at this, the source goes into the inputs of the broadcast, and then I can define separately the output path of each of those branches. So I'm going to say, okay, for the first output of the broadcast, go to the even flow, and then to one of the inputs on the merge. And then on the other output from the broadcast, go to the odd flow, and then that's going to go into the merge. And then the merge will get into the sync. All right, so I forked it, did some parallel operation, and I'm going to bring it back again. And then down at the bottom, once I have my graph, I can run it, and then that's going to yield the results. So if we execute this again, okay, at the bottom there, you can see where the count is even and odd. So out of the, I think I submitted, it was about 1,000. Out of 1,000, I got 492 that were even and 508 that were odd. Does that make sense? Any questions on that one? Yes. Yep. Okay, great question. I'm going to repeat that to make sure I understood it. So on line 55, I say the output of the merge goes to the sync, but I didn't have to do that on line 56. Is that the question? Okay. The reason I don't is because with the DSL, once I've connected to an input, I only have to do that once. So I've taken the same instance of that merge connector, and I've connected it to the input of the sync. So later, when I pipe stuff into merge, it's already got a connected output. So the output of the merge is already connected once. I could easily have put that, I could easily do this, and my code still work. And so what I've done is I've said, okay, even flow goes into merge, odd flow goes into merge, and then I'm going to connect the output of merge into the sync. And the DSL is kind of hiding the input-output terminology there, but if I were to not use the DSL, I would have to say, okay, on the merge object, dot output or whatever, pass in an instance and all that. Is that clear? Okay. Any other questions? All right. Okay. So one thing that akka-streams does really well is handling parallelism and asynchrony. And so by default, akka-streams uses what's called a fused workflow. That means that one actor is going to be allocated for the entire graph. So if your actor is connected to a single thread pool, you're essentially going to have one dedicated thread that is going to run on that workflow. So one at a time, messages will go across. With asynchronous boundaries, you can have parts of your workflow run on their own actor. And so if you have one part of the workflow that's kind of doing something computationally heavy, there's no sense in the other half of the workflow waiting on that guy. You can go ahead and have it processing. So let's say you might have a really heavy process that runs, then a buffer that's gathering in the middle, and then that buffer is going to be sent to something that's like writing to a slow network somewhere. You can go ahead and once that buffer is full, have that part working on sending to the network while the upstream is gathering and doing the heavy computation. So what you can do is you can specify asynchronous boundaries, and what that does is every time you have an asynchronous boundary, that part of the workflow is going to get its own dedicated actor on the actor system. So if you're familiar with the actor system and you're familiar with the thread pools on the actors, there can be some performance gains in separating your asynchronous boundaries. The penalty here is that there is a cost marshalling data from one actor boundary to another. So in the example I have, I'm working with a very small amount of data, so the time savings is almost negligible because it is expensive to go from one asynchronous boundary to another. But if your operations take longer than that little payload of marshalling the data, then there could be some significant savings on how you do it. So you got to kind of play with that to see what makes sense. So here's an example of using asynchrony. So let's say we're going to perform factorials on integers. And the factorial is kind of an expensive mathematical operation. It's going to recursively, run through the list. Let's see here. So what I'm going to do is I'm going to measure the start time of when my workflow starts. I'm going to emit a bunch of random integers. I'm going to apply a factorial function on those. And then I'm going to add an artificial delay in the workflow now. And the reason I'm adding the artificial delay is just to kind of slow it down so that I'm generating kind of a slower upstream and a faster downstream, just to kind of show how the asynchronous boundary might help here. And then I'm going to drop in this async. I'm actually going to not do that this first run, and we're going to see what the time difference is. And then on the other side, I'm going to run it through the factorial again, add in another delay, and then throw that into the sync. All right, so long operation with the delay, another long operation with the delay, and then I'm going to fold everything together. Oh. This is going to take just a minute, which is why I wish I had some good jokes here. So while we're waiting on that, what this is going to do is right now, since I don't have an asynchronous boundary defined, this is going to be what's called a fused workflow. So this whole workflow is going to run on a single actor, all right? And so essentially, it's going to take, the demand is going to be one record at a time flowing through here, the whole thing. So every time it hits a delay, that's going to halt the demand until that delay is sated, and then it'll go to the next place. Okay, so that took about 14.7 seconds there. Okay, so let's add in the async. So what I'm doing with this, let me go ahead and run it. What I'm doing with this is I've created the async boundary, so this part of the workflow is going to run on one actor, and this part of the workflow is going to run on a second actor. And so that means that depending on how I've set up my thread pool, each of those can share the thread, and so one can work while the other's waiting, and then it can switch back and forth. Okay, bummer. That actually took a little longer. Last night, it took faster, so that's kind of a bummer in the middle of a demo. The reason why it takes longer in this case is because, like I said, the operations are so fast that this is actually the cost of marshalling between the actors. So we could try bumping up our delay time to see if we can simulate it going faster, but it may not work out that way. Thank you. Yeah, it should use, so the actor system uses messaging, so you have like a mailbox where it can send messages. So when there's communication between actors, it's typically converting those into messages to go from one mailbox to another, if that makes sense. So yeah, so it's kind of got its own internal messaging. I think, Dylan, is it communicate the messages through, is it a binary format? There's going to be references on the JVM? Okay. All right, I set my delay too long and my time ran out. All right, well, we'll call that a failed demo. But essentially, what you're doing here is you're creating to where both sides can kind of work independently of each other. So if I was doing something not trivial, because right now I'm just doing a couple simple integer calculations, which is really quick. The marshalling here takes a little bit longer, but if I were to do something that was substantial, like write to I/O on both sides, that would parallelize a lot better. All right. Okay, now here in my opinion is where we have a really big benefit of the akka-streams system is enterprise integrations. So when you're working with larger data platforms, you want to be able to naturally hook up to all kinds of different endpoints to receive and push data. And the nice thing about the akka-streams API is that a lot of the ones that you might commonly write to, it already has connectors for. So there's a couple projects out there. One of them is the Alpaca project. So if we were to go to that website, the Alpaca project has pre-built connectors and akka-streams for all kinds of different systems. So you just kind of look through the list here, but you've got AWS, Cassandra, CSVs, File, FTP. It's got some Google Cloud stuff, HBase. You get the idea, S3, SQS for the AWS notification stuff. So that's a pretty cool project. So if you're interested in using akka-streams and you're connecting to one of these systems, you might look into this project, which already has pre-built connectors to use, which is very helpful. And then the other thing, since I said at Augsburg we use Kafka, there's what's used to be called Reactive Kafka. They've recently changed the name to akka-streams Kafka. And this is an API, a connector for Kafka consumption and production, which is quite nice. So it comes with a custom producer and consumer that already works with the stream handling and takes care of the offset committing for you. And so you kind of still have the control of how the offsets are committed and stored while still getting the streaming semantics. So I'd like to show a demo of that. So what I have running on my laptop right now is I hope it's running still. I'm using Docker. I've got a Zookeeper and Kafka cluster running on my laptop. And then I've got an error because it died out. 1 second. Let me restart my cluster here. But essentially, I have a cluster that's running, and I'm going to have akka-streams. I'm going to have a producer that I can type into and produce messages, and then that will automatically kind of live flow through the system. All right, I think that's running. I think we're good again. All right, so here's what the API looks like for this. I'm not going to go into all the details about this API because it's really specific. If you use Kafka a lot, some of this will be familiar. If you don't, it may not make a lot of sense. I'm not going to spend too much time on it. But there's different ways to consume from the Kafka consumer. You might want to have auto commit enabled and just consume messages as fast as you can, or you might want to handle the offsets and how that's committed. So there's different ways they have of doing that. But what I'm saying in this example is I'm going to consume from this topic, and I get my message in this map function, and then I can do whatever I want with that message. In this case, I'm going to just print out some details about it. And then I'm going to batch those up. So I might say, okay, I'm going to introduce a batch in the middle of the workflow so my upstream and my downstream can kind of work on a larger load. And then I'm going to commit that batch all at once. So it's pretty nice. Let's see if we can get this to actually work. Okay, so now it should be, if everything's working, should be sitting here waiting for this always happens right when I'm doing this live. No. Thank you, Dylan. Okay, so now it should be listening. And so we can emit messages here. So we could say waffles. And if we're working, we can see right there at the bottom that it got the message with the offset. So we can keep going over here and we can say name 1, name 2, name 3, 4. And it's just going to keep getting those live. And so they just kind of stream in. So I've built the graph, and now that the graph is open, you can have Kafka messages just flowing in and out. And so your service, like if you're doing this on a microservice architecture, now you've just got your graph that's a simple pass-through, which is really nice. So you just use that DSL, create just what the middle piece looks like, and have each one of those in their own little microservice. We use Docker containers to host it all, and then you can just have messages ripping through your whole workflow end to end with all the streaming set up, which is pretty nice. Okay, any questions? That's what I got today. Any questions about that?
You talked about a scenario where suppose that batch pattern we get up from one source and make the rest call, and I get a suppose
Mm-hmm.
I can put this stream, take this stream in between bit of buffer.
Mm-hmm. Sure. So the question was, one of the examples I gave earlier was whenever we might be loading a lot of data and wanting to push that to a RESTful endpoint, and eventually the RESTful endpoint might get overwhelmed depending on how many requests it can handle, and so you need to throttle your request to that endpoint. So how would this help in this case? So in this particular case, what you would do is writing to that RESTful endpoint would be an operation in the workflow that would give back pressure. So if you know that, okay, I can only push to that endpoint, then you can add like a throttle into your stream. So actually, let me show you the API real quick. This is pretty helpful. So on a source in the akka-streams, there's a whole lot of functions for controlling the stream rates. And one of those is a throttle. And you can define a throttle in several ways. You can say, okay, this particular operation downstream has a cost associated with it. And so it can kind of figure out like throttling based on the cost. Or you can say, I only want you to emit so many elements against a particular timeline. So here's a finite duration that you need to throttle. And what that does is that signals upstream. It controls the demand and says, don't issue anything else from upstream until this particular time has lapsed. So that's one way you could do that. And it kind of depends on, and some of that would depend too, like on how you know if you're going to overwhelm that web service or not. You can also, in the actor system, lean on some of the exponential backoff stuff. So if you start to hit it at a certain rate and you still get failures back, then you can kind of back off that throttle rate so there's a longer delay in between. Anything else? Okay, well, thank you.